Okay, chapter 7 review. Again, don't worry about these ones. There's different ones at the end. The initial value problems, we did some of them and we skipped others, but we're going to do this one. The initial value problem, basically it just gives you values so you can figure out what C is, because it's going to give you a derivative. You want to find the antiderivative and then you plug this in to figure out what your C would be. So I'm going to rewrite dy dx. 1 over root x is the same as 1 over x to the 1/2. So I'm going to write that as x to the -1/2 instead, and then minus x. So then if I'm doing the antiderivative, this would have started as a positive 1/2, and then that would have come down and it would have had to multiply with a 2 to make it turn back into a 1. And then this guy, it would have had to be a x squared. That would have come down and multiplied with a 1/2 to turn into just a -1. Okay, and then plus c, so that's what we're solving for, and we're going to plug these values in. So we're plugging in y at 2, so that's our x, and this is our y, so 3 is equal to 2. Okay, so this is 2 root 2. 2 squared is 4, divided by 2 is 2, plus c. So then c, if I move this over, that's 5 minus 2 root 2. So 5 minus 2 root 2. And because we want to keep this as exact values, we're just going to leave it as that whole thing. So we've got 2 root x minus 1/2 x squared plus 5 minus 2 root 2 as my overall derivative, or sorry, antiderivative. Don't worry about Euler's method. Slope fields we did talk about, so the slope field for which differential equation is below. So this is pretty light, but you can see, hopefully I'm gonna make some of them a little bit more visible, but it is pretty light. That looks like everything's constant at y equals like across any y, right? So they're getting steeper as we move up our y, but everything like across a row is the same. So it's probably going to have a constant y. And then the other thing that we can see here, or that we can't see, are these when y is equal to 0, our slope is 0. Okay, and then basically as we see it going up, as we get closer to 1, our slope gets steeper to like a 1. Then it gets steeper to a 2, to a 3. We've got negative slopes, steeper negative slopes, even steeper negative slopes. So definitely it's like y. And because it's at 0, it's equal to 0. It can't be y plus anything. It just has to be this guy. So we can kind of do it process of elimination. So my reasoning for this was when y is equal to 0, slope is equal to 0. And that's the only one of these that would work for, okay? And then if y was equal to 1, slope was equal to 1. So we see that pattern. If it tells us to use substitution, we need to figure out what our u is going to be. So in this case, because I've got a quadratic and then a linear function, I know that the derivative of a quadratic is going to be a linear. So I'm going to try it as x squared plus 4x minus 12 is my u. So then my du dx is going to be 2x plus 4. So then, like that. So I've got u on the bottom. So And remember that this is x equals 2 to 3. So I've got u on the bottom. And then notice how I've got x plus 2, but over here I've got x plus, or 2x plus 4. So if I factor out a 2, then I'm going to have du is equal to, I'm just going to have an x plus 2, divide both sides by that 2. Oops, this should be a dx, my bad. So that 2 comes out, we divide it out onto the other side, and then this is what we want to replace. So then we have du. So remember when we have a 1 over u du, or a 1 over x dx, or 1 over something d whatever that something is, this is always going to be, the antiderivative is going to be log, or sorry, a ln. It's a natural log. Okay. Oh, and I forgot the 1/2. Oop-a-doo, because this should have been du over 2. So that 1/2 can come out. We'll do it like that. And then we actually did the integral, so we don't need that. Ln of u. And remember, this is from x equals 2 to 3. So we either need to plug this whole thing back in, or we can figure out, okay, if I plug a 2 in for u, what can I plug in, or for x, sorry, what can I plug in for u? So if I say, okay, well, u is equal to 2, then that's 2 squared plus 2 times 4 minus 12. So 4 plus 8 minus 12, that's 0. So it's going to be 1/2 ln u from 0 to, if x is 3, 3 squared plus 4 times 3 minus 12. I reversed the order of these guys, sorry. So 9 plus 12 minus 12, these guys cancel, so we get 9. So then we're going to have 1/2 ln 9 minus ln 0. So we can leave it like that. Remember that ln, we shouldn't box this one. Remember that ln, if we think about the domain of this, a 0 can't go in. So this is going to be non-existent. So it's just 1/2 ln 9. Okay. And then antiderivative of this guy using parts, and we're going to check it using tabular. So remember that we want to pick a u that we can do an easy derivative of, and we want to pick a dv that's an easy antiderivative or integral. So I'm going to say u is this part, because we always kind of want to get rid of whatever we pick as u. So we want to pick stuff that's going to like drop powers and go away. So then du is going to be 2x minus 5, and then if I started with the dx over here, move it over there. Then dv is e to the x dx, and we know that the integral of e to the x is just itself. Okay, so we set up the substitution. So this whole thing is equal to u times v, so x squared minus 5x times v, so e to the x, minus the integral of v du, so v e to the x du, so 2x minus 5 dx. So notice how instead of now having an x squared, we have an x, so we're getting there, but we're going to have to do another iteration. So now u is going to be this 2x minus 5. du is going to be 2 dx. v, or dv, sorry, is e to the x dx again, and then v is just e to the x. So this whole part is going to stay, so we've got e to the x times x squared minus 5x minus bracket. So u times b. So 2x minus 5 times e to the x minus the integral of v du. So e to the x times 2 dx. So now, if we take that 2 out, we just have the integral of e to the x dx, which is just e to the x. So we're going to have e to the x, it's x squared minus 5x, minus e to the x times 2x minus 5. And then the negative is going to distribute, so this is going to turn into a positive 2 e to the x. Okay, so, and then we have to add our plus c, which we didn't, oh no, we didn't need it up here because we had boundaries. Haha. So there is our antiderivative. To check it using tabular, remember that we're going to start with our x squared minus 5x on one side, and we're going to start with our e to the x on the other. So this side we're doing derivatives, this side we're doing integrals. So 2x minus 5, 2, 0, e to the x, e to the x, e to the x. That one's super easy. And then the top one on the right side doesn't matter, the bottom one on the left side doesn't matter. And then we match diagonally, positive, negative, positive. So this is going to be e to the x times x squared minus 5x minus e to the x times 2x minus 5 plus e to the x times 2, and then plus a constant. So same thing. So we win. Okay. Here are the questions that you guys should be doing as practice. We'll have a Q&A, so if any of these are issues for you, let me know tomorrow.